Hi everyone, my name is Vivian Chen and I am with my colleague Kayla Bogus. We're from the University of Virginia and we will present our recent work on towards transparent robotic planning via contrastive explanations. In recent years, we are seeing more and more black box robotic systems that usually gives lay users little understanding of how a decision is made or why an action occurs. This often leads to misunderstanding and mistrust of the system. The majority of work in explainable AI has been focused on the building of simplified interpretable models as approximations of complex decision-making functions. However, few works consider social science theories of explanation. In this work, we are drawing insights from Tim Miller's work about social sciences about explanations, where he pointed out people are more interested in contrastive explanations that asks not why event P happens, but why an event P happens instead of some event Q. We also incorporated other concepts like selectiveness, which is about choosing the most relevant events, constrictiveness, which is about numbering future possible actions and flexibility, and responsibility, which is about deciding how important an action is compared to its alternatives. We can see now we have knowledge about a robotic system and the human preferred factors, but how do we link them with appropriate explanations? We want to answer with our contributions in this paper, where we first formalize the notions of selectiveness, constrictiveness, and responsibility in mathematical terms, and then we present methods to automatically generate contrastive explanations with these key factors. And finally, we conducted a user study with 100 participants on Amazon Mechanic Turk to investigate user understanding, trust, and preference about the generated explanations. For the motivating example, consider a route planning example in urban areas, with white blocks representing highways and yellow ones represent alleys. There are three possible routes from S to D highlighted in red, green, and blue. Each route has its pros and cons. For example, the red route is on the highway the whole time, which is safer but longer compared to the blue one. That is in alleys most of the time, which runs a greater risk of collision but shorter in distance. Then the question is, how do we explain the route choices to a lay user? Of course, we can naively show the actions taken at every state, but that would be tedious and even infeasible in larger models. Therefore, our approach here is to select a handful of critical states and only explain actions on those. Also, we not only explain what action to take, but also why that action is taken by comparing it to its alternative actions in terms of constrictiveness and responsibility. We have said selective is about choosing the most relevant events. This is important because it can potentially ease the user's cognitive burden. To be selective, we define a set of critical states where our states the choice of action would greatly affect MDP policy and performance, then only explain at those. As you can see in the animation, the resulting amount of explanation is obviously smaller, even for this small example. Knowing where to explain, now we will focus on what to explain. We chose constrictiveness and responsibility here. From social science, a decision is said to be more constrictive if choosing it causes fewer possible future decisions. And naturally, as the robot approaches the destination, the decision will be more constrictive, as there is no decisions left to make. So we only compare this property for actions at the same starting state. Mathematically, we define this value to be the number of enabled actions at future critical states, as shown in the animation here. The value for going east at state 10 is 4, whereas that of going south at the same state is 2, which shows east offers more flexibility to make changes. Responsibility is about the relative influence a decision exerts on the final outcome, and humans are usually interested in the more responsible decisions. In our definition, responsibility needs to be discussed based on the objective at hand. For example, we consider the objective of the distance to destination. Then we can compute the total expected cost for going east and south. Since a smaller value for this objective is desired, the less responsible action, going east, is actually preferred here. Kayla will talk about the generated explanations and the user study.
Once we've mathematically defined each contrastive explanation concept, we create a corresponding explanation for each. As you can see, the responsibility explanation deals with explaining why the action occurs, while the constrictive explanation shows the flexibility of the action. The presented selective explanation shows only the most important states in the route. Our contrastive explanation combines all three of the previous factors and points out that this action is taken instead of other options. Each explanation has a naive counterpart to present with it. We then performed a user study where we presented 100 users with 3 maps like the one shown in the upper right. All the maps were approximately equivalent, and highlighted the shortest route. We wanted the maps to be big enough that the user couldn't just look at the map and tell what the shortest path was. They would have to interact with the explanation. The users were asked to evaluate the explanations on how much they understood the information presented, how much they trusted the explanation was correct, and if they preferred the explanation. We also measured the amount of time the user interacted with the page the explanation was on to measure a potential cognitive burden that the explanation would cause. In terms of understanding, we found that users understood any explanation over no explanation as expected, and that users understood the responsibility and constrictive explanations more than their naive counterparts. However, users understood selective explanations less than their counterparts, showing that explaining more states leads to higher understanding. Contrastive explanations showed a combination of all three factors in terms of understanding. They are more understood than selective explanations, but less than responsibility or constrictive. In terms of cognitive burden, having no explanation greatly increases the amount of time needed to interact with the explanation. Responsibility and constrictiveness perform better than their naive counterparts, and selectiveness shows a trade-off between the number of states explained and the amount of burden placed on the user. Finally, contrastive explanations fare quite well at reducing cognitive burden. Finally, looking at trust, we see the same patterns repeat. Responsibility and constrictive explanations perform better than their naive counterparts, while users trust explanations with more states over only the most important ones. Overall, contrastive explanations fare relatively well at increasing user understanding and trust while reducing cognitive burden. In terms of user preferences, we found that users preferred responsibility and constrictive explanations over their no or naive counterparts. As expected, users also preferred naive explanations over their selective counterparts. However, comparing all 4 of the explanations we created, we found that users preferred all 4 explanations at about the same rate, with a little more lead to contrastive and a little less to responsibility. This is interesting, as responsibility explanations provide the highest understanding and trust, showing that users might not prefer an explanation even if it is the best for the situation. In conclusion, we found that the social sciences provide usable insights to increase understanding and trust in explanations. Specifically, selectiveness, constrictiveness, and responsibility are viable ways to increase these factors or decrease cognitive burden in these situations. Finally, we find that users have a diverse set of preferences, and that just because a user prefers an explanation does not mean it is the best for the situation. We'd like to thank you for attending our presentation. You can find more technical details in our paper if you'd like, but please feel free to contact us with any further questions. Thank you and have a good day.